In question 2a, we're asked to define the capacitance of a capacitor. Well, this is defined as the charge stored per unit potential difference. In B, we have a circuit diagram containing a battery, a resistor, a capacitor and a switch, along with a graph of charge in microcoulombs against time in milliseconds for the circuit when the switch is closed. In part 1, with the capacitor fully charged, it stores a charge of 13.2 microcoulombs. The EMF of the battery is 6 volts. We need to find the capacitance of the capacitor. Well, capacitance is charge over potential difference. Putting in the values gives 2.2 microfarads. In part 2, we're told the time constant is the time taken for the charge stored to increase from 0 to 63% of the final value. We need to use the graph to find the time constant in milliseconds. Well, 63% of 13.2 microcoulombs is 8.3 microcoulombs, and reading from the graph, this occurs at 15 milliseconds. In part 3, we need to find the resistance of the resistor. Well, time constant is also equal to capacitance times resistance. Rearranging, putting in the values, gives 6820 ohms. In part 4, we're asked what physical quantity is represented by the gradient of the graph. Well, the gradient gives the rate of change of charge with time. This is current. In C part 1, we need to find the maximum value of the current in milliamps in this circuit during the charging process. Well, this will occur at the start, and current is potential difference over resistance. At first we have 6 volts over 6.8. At the start we have 6 volts over 6820 ohms, giving a current of 8.8 times 10 to the minus 4 amps, or 0.88 milliamps. In part 2, we need to sketch a graph on the outline axes to show how the current varies with time as the capacitor is charged. We need to mark the maximum value of the current on the graph. Well, the current will start at a maximum of 0.88 milliamps, and it will drop something like this, reaching 0 at around 60 milliseconds.